Okay, we're going to talk about the iterator adapters and container adapters, and we may or may not get through all of them today. We'll start with iterator adapters and see how far we get. And then we're going to take a sort of a foray into our discussions about functors. And then once you've understood functors, we're going to come back and explore function adapters. So it doesn't really make any sense to talk about function adapters until we've talked more about functors. And we haven't really talked in great deal about functors yet. So what we're going to do now is we're going to start a discussion with STL iterator adapters. So there are many STL algorithms that copy the elements that are passed via an iterator. And that iterator indicates where in the container to begin doing the copying. And some examples of these algorithms would be, of course, copy, which I show here, unique copy, copy backwards, remove copy, replace copy. There's a whole pile of such and such underscore copy. So, and then there's, remove copy if, replace copy if, and so on and so forth. And in all these cases, one of the things that you need to do is indicate where you want the elements to be copied into. And that's why I have this little question mark at the bottom. So, of course, if you're going to be copying from an input range into some output iterator, you really need to know how big to make that output iterator, or you need to make sure that, whether you know or not, that it can be big enough to hold all the elements in the input range. So here's, again, a little example I show you on the right-hand side, where we've got the copy algorithm, which you've now seen many times, and we've got ourselves a vector that we want to have the contents of standard input copied into, but that raises the question, how big should we make the vector? And obviously, if you make it too small, you'll end up with a bounds checking exception. If you make it too big, then you've wasted memory. So how can you make it just right? That's the question to wrestle with. By the way, I should also point out real quickly that one of the things you guys should start doing in your assignments is using the copy algorithm, using other STL algorithms like fill and equal and so on, in order to perform some of the steps in your implementations. So there are lots of places where people are writing for loops to copy the contents of one array to another. You should try to see if you can use the copy algorithm instead, which will be going to make your code a lot cleaner. That's just a little aside, however. So what we're going to do here is we're going to use an iterator adapter. In this case, we're going to be using something called a back inserter in order to be able to expand the containers as the algorithm is performed. And so what we're going to see, this is going to be an adapter that'll take a container and then be able to adapt it to work as if it was an iterator, in this case, an output iterator. It's also worth pointing out, by the way, that I'm also illustrating some other adapters here as well. So iStream iterator is an iterator adapter that takes cin and makes it work as an input iterator. And we'll also, of course, talk about those things as well. So the way this is going to work is we're going to start out with an empty container, because we don't really know how big we want it to be until we go through the input range, and that could be coming out of a file as it is here, so we don't really know at the time we create the vector how big to make it. And then we're going to use the back inserter to grow the underlying container as needed. And you can imagine what back inserter is going to do is it's going to call pushback on the vector, and that will automatically allow the vector to grow as more and more elements are added to it. Okay, so I'm going to show you some examples now that are going to talk about these different adapters, and we're going to talk about back inserter and front inserter and inserter and so on. And they all have sort of the same variation on a theme. What they're going to do is they're going to go ahead and create what looks like an iterator from the point of view of an algorithm like copy, in this case, an output iterator from the point of view of an algorithm like copy. But under the hood, that iterator adapter is going to call the appropriate method on the underlying container in order to add the element in the right place. So, of course, a back inserter will call pushback. A front inserter will call push front. An inserter will call insert, and so on and so forth. And so you get a chance to see how all these different mechanisms work. And as usual, we'll walk through source code, and I'll try as much as I can to peek down inside to see what STL is doing under the covers. So let's start out with just an overview of what iterator adapters are. And what they're really intended to be able to do is be able to do several different kinds of characteristics. They can be used to take containers and then allow us to insert elements into them using things like the copy algorithm or variants of that. There are going to be these other things called reverse iterators that take forward iterators and make them go the other direction. And then there's also something called stream iterators. And we've seen examples of some of these things already, but I'm going to go through them more systematically now. So let's start by talking about insert iterators. These are also sometimes called inserters. They allow you to wrap a container in such a way that the insert operator, the assignment operator that's called in a generic constructor or generic algorithm like copy, can be used to transparently forward to the appropriate method in the container that will add the element to either the beginning, the end, or some other arbitrary location in the container. And what's important to remember about all these adapters is what they let you do is they allow you to insert elements rather than overwrite existing elements. And that'll become important when we look at some of the examples here in a second. Now, as you'll see, there are three main types of these insert iterator adapters. They are the front insert iterators, which put things at the front of the underlying collection or container. There's back inserters that put things at the end. And then there's inserters that put them wherever you want them to put them. You can indicate where you want them to go. And each of those different inserters work in different ways on different types of containers. So you can see here, for example, that the front insert iterator is going to call the push front method on either deck or list, which support efficient adding at the beginning of their container. Likewise, the back insert iterator is going to call the push back method to put an element at the end of the collection or the container. And here we have various containers that have a pushback like vector, deck, list, and string. And then the final class or final type of insert iterator is the insert iterator. And this uses the insert method that will put a value at a particular position. And all the various containers that we care about, like vector, deck, queue, map, set, and so on, those all support the ability to be inserted. So it turns out that only deck and list support the ability to do front insertion through push front. Only vector, deck, list, and string support back insertion, but all the vectors, including multi-set and map and multi-map and unordered set and all that good stuff, they all support the ability to do inserts. And this is important because there are lots and lots of algorithms in STL like copy and so on that all require this ability to basically assign something into an output iterator. So what's really nice about this is this allows you to have an initial container that is not given a value at all. It's empty. And then you can use these insert iterators to adapt that container so they get just as big as they need to be without you having to know in advance how big that should be. So we're going to start out a discussion of insert iterators by focusing on back inserter, which is arguably the most common insert iterator. And the reason for that is that vector is the most common container, and back inserter works very well on vector and other things like it, like deck, by calling the pushback operation when the assignment operator is called in the copy algorithm. And the argument that you pass to back inserter is the container itself. So here's what back inserter looks like. You can see that back inserter is a generic function that's parameterized by the type of container. And what it does is it goes ahead and takes a container passed to it by reference, and it makes an instance of a type called back insert iterator. And we will take a look at back insert iterator here in a minute. And so this instance of back insert iterator is going to hold the container by reference. It doesn't actually copy it. It just holds a reference to it. And what it's going to do is it's going to return a back insert iterator that wraps that container. And then operations that are done on this by the copy algorithm or unique copy or replace copy, or whatever you're doing that requires an output iterator, will end up calling overloaded methods, overloaded operators on the back insert iterator object, which will then have the desired effect. The most important of these is the assignment operation, which will go ahead and insert the next element at the end of the container that's being held by reference. And we'll take a look at that when we get a little bit further along. Now, you might ask the question, why is there a function called back inserter whose only purpose in life is just to encapsulate the creation of a back insert iterator object? And the reason for that, of course, is that with STL, you can have type deduction of function parameters. The compiler can figure out what you mean, and it can do the right matching for the right template. Whereas for structs or classes, it doesn't work that way. So structs and classes don't allow you to do this. They don't do deduction of the types. However, the functions do allow you to do deductions of types. So first I'm going to show you kind of the bare bones way of doing this. Now, nobody would ever do it like this. This is just showing you what's going on under the hood. So we're going to define ourselves a vector of int that's initially empty. We're going to make an explicit instance of a back insert iterator object that's parameterized by vector to int, as you can see here. And we're going to call that n, very unimaginative name. And then I'm going to go ahead and pass a reference to the vector to the constructor of object n of type back insert iterator vector of int. It's a bit of a mouthful. And then what I'm going to do is I'm going to walk through for, I'm going to basically walk through standard input, and I'm going to go ahead and store each int in the standard input into my back insert iterator. And I'm going to use the star and plus plus operation to give the illusion that I'm actually going through this thing and kind of incrementing the iterator every time through. So that's the way that you would read the input in and then go ahead and write the output. Here's, of course, the more canonical way of doing this. So most people would write the code I have if-def out here. You would not write the code I showed you there, although that's what it's actually doing under the hood. So what you would do here in practice is you would go ahead and use the iStream iterator to read the contents from the standard input, and then you would call the back inserter in order to be able to add that to the end of the vector. So let's go ahead and take a look at what back inserter does. And you'll see what back inserter does is it basically does what we're doing here, except it hides it behind a nice function that can deduce the types. So we don't have to write something hideous like this, which is very verbose and tedious to have to type. All right, so let's go ahead and see if we can find the implementation of back inserter. So if you take a look here, here is the implementation of back inserter. And what back inserter does is, as I showed you before, it takes a reference to a container, and then it makes an instance of back insert iterator. And you'll notice that it's deduced the type of the container. So now the function has figured this out. You don't have to write it explicitly. And then we go ahead and pass in the reference to the container here. So that's the back insert iterator. Here now is the actual back insert iterator class. So you can see back insert iterator is a class, and it's going to have a pointer to a container that it stores as a data member. And then it's going to have a bunch of constructors. In this case, this is the one that we were just calling, this back insert iterator constructor, which is what's called, of course, from the back inserter function. It goes ahead and takes the container and it stashes the address of the container in that local field. Okay, so far so good. The most important method in back insert iterator is this one, operator assignment. And you can see that when operator assignment is called, what it does under the hood is it goes ahead and it calls pushback on the container with the value that's passed as a parameter here, as a constref, to operator assignment. And if you think about the way that the copy constructor works, it's not the copy constructor, the copy algorithm works, it's going to go ahead and copy whatever the front or the first iterator is looking at, and it'll assign it to the output iterator, which in this case is adapting around the container, which is calling pushback on the container. Now, what's interesting about this is if you look a little further down here, you can see that there's a bunch of other operators like operator dereference, operator plus plus, and so on. And those are complete and utter no-ops. They do nothing at all. And their only purpose is just to hold the syntax of the copy algorithm to work properly. But in fact, the only thing that does any real work is the assignment operator. Everything else is just there to look pretty. So if we come back over here to the main program where we're using this stuff, you can see that this call here where we did star n++, you could actually have written it like this, and the code would have still worked exactly the same, because the thing that matters here is not the star or the plus plus, it's the assignment operator. And that's where all the magic is getting done. And so that's what's actually going on in the copy algorithm. I won't bother trying to follow through copy because it's lost in a mist of convoluted codependencies and inner method calls within the STL implementation. But if you go back and look at copy from the slides, you can see exactly what it's doing. So that's what back inserter is doing. It's basically taking a vector, making it look like an output iterator, and then arranging to have its pushback method called in order to be able to add the next element in the range that we're getting from the input iterator into the collection. So here's another example. This shows how to use a back insert iterator to add elements to a container rather than overwriting them. Now, this was also shown in the previous example, but we didn't talk about it in as much detail as we're going to talk about it now. So here's the use case. We start out with a vector and we add elements 0 through 4 to it. And so we could have done this. We could also have done this like this. We could have done 0, 1, 2, 3, 4. Maybe that's a better way to do it. A little bit more concise. So let's get rid of that. And then we're going to go ahead and print the contents of the first vector. And now what we're going to do is we're going to make a new local variable called back iter. And maybe it would be better to rename this to something that's not quite so convoluted. So let's see if we can do that. Let's go ahead and refactor this guy. Let's just call it iter. That's a better name. And so now we have an iterator, and what we're going to say is star iter plus plus equal 100, star iter plus plus equal 200. And what that's going to do is it's going to actually cause 100 and 200 to be inserted into the vector, potentially growing it if necessary, rather than overwriting what's already there at that location. And I'll come back after I run the program. We'll come back and take a look at what it does. So now we go ahead and print the results after we insert 100 and 200 into the iterator. And then we go ahead and print the contents, both of vec2 and vec1. So you can see also here, we're going to copy the contents of vec1 into vec2 using back inserter, and then we'll print the contents of everything after we're done with that. So let's run this program. This will actually produce some output, and we can talk about it. So you can see here's the original contents, 0 through 4. And then after we do the insertion, you can see that we now have 100 and 200 at the end because we used pushback. We used the back insert iterator. And then we had the size of vec2 before we did the copy, which was 0, of course. Then we do the copy, and then we print the contents of v2. And of course, lo and behold, it's now got the same contents that v1 has. And if I want to, I could also do something like this. I could say, if equal avec1 dot begin, avec2, or say avec1 dot end, avec2 dot begin. What I'm doing here is I'm using the equal algorithm to say cout vectors are equal, which is what we expect. And then I can also say, if it doesn't end up being true, then I can say cout end of the world, because there's no reason that they shouldn't be equal after we just did that copy. So let's go ahead and have some fun and rerun this. And it hopefully come back and say the vectors are equal. Yes, it does. It's not the end of the world. So that's just illustrating yet another STL algorithm that can be used to compare two ranges of the same size for equality, which of course should work in this case. So let's go back and take a little bit longer look at this stuff. So you'll see here that this is using my back insert iterator, and because it's going to be doing pushback, it's going to put it at the end of the vector. Now, as I mentioned before, this star plus plus stuff is just there for syntactic sugar. It's just there so that the copy algorithm will work properly. But I can take those things out entirely, and I can run the code, and lo and behold, I get exactly the same results I did before. And that's because only the assignment operator is actually doing anything useful. Everything else is just there as a way to make the syntax work for algorithms like copy that expect to be able to do dereference, which is the star, and increment, which is plus plus. So that's pretty cool. Otherwise, we would have to write different code and it would get convoluted. So this is a great example of the adapter pattern, which takes two things that weren't really designed to work together, namely the copy algorithm and a vector, and then adapt the vector to have the interface that's expected by the copy algorithm. So that's just classic adapter pattern at work. And you'll also notice here that because this is an iterator adapter, it doesn't overwrite the contents of the elements that we have here. Again, just for kicks here, let's try something else here. Let's comment this stuff out, and then let's say auto iter equals, and let's say avec1.begin. So now, if we do this, we're going to get a different result. So let's take a look. Now the end of the world probably will happen. We'll see if it does. Yep. You can see what happened now is after we used when we had a regular good old iterator to this, as opposed to a back insert iterator, what happened when we got an iterator to the beginning and we said star iter plus plus, it actually overwrote the contents that are in the vector as opposed to enlarging them by pushing them at the end. The other thing you'll notice here is that they ended up showing up at the beginning as opposed to at the end. So clearly, if we do it that way, then we're not adapting anything, and we're also just overwriting the contents as opposed to having this inserter that inserts the elements, and in this case, it's going to insert them at the end. So hopefully that also kind of clarifies a few things about how these inserter adapters work to add the elements to the container as opposed to just overwriting the contents. So this example is going to kind of look from a different perspective. So far, we've been talking about back inserters, and we've been focusing primarily on vectors, although we could also have used dex, but I've been using vectors just to make it simple. Now we're going to take a look at front inserter. And as you might expect from the name, a front inserter is going to cause the adapter to put things at the beginning of the container, not at the end. And in fact, what it's going to do is it's going to call the push front operation. And this inserter can only be used with list and deck containers because you can't call push front on vector because it doesn't support that method because it's not meant to be efficient to put things at the front of a vector. So here's the front inserter function template, and let me get rid of this one. We don't need it yet. We'll talk about that next. So you can see here that front inserter is like back inserter, except it creates a front insert iterator. And as you might expect, the front insert iterator is going to do a push front instead of a push back. So here's the example we're going to use. We're going to have a list, and we're going to have an iterator here. And let's see if I can get around. I guess I don't actually even use this iterator, so we can get rid of that guy. Then we're going to go ahead and add a bunch of elements to this list. We're going to go ahead and add them there. And it's probably not a half bad idea. I gotten tired of writing these loops. Originally, I was into writing loops because that's what you could do back in the earlier versions of C++. But once the concept of an initializer list came along, there's really no need to write these silly loops anymore. So we print the contents of the list. Then we're going to make ourselves a front inserter. And let's go ahead once again and just kind of clean that up. I think that's a little bit too verbose, so let's call it iter. And then you're going to see here that when we say star iter plus plus, it'll add the elements at the front, sliding the other ones down, of course, rather than overwriting things. So again, as we talked about before, if we had said auto iter equal a list one dot begin, if we'd done that, and of course commented this out, we actually would get the same, we wouldn't get the same behavior because we would have overwritten the first two elements as opposed to adding the new elements in there. Okay, so let's go back here to this thing. So that'll insert them, then we'll write the results. Then we're going to go ahead and copy everything from a list beginning to end, and we'll put it at the front of a list 2, and then we'll go ahead and write the a list 2 when we're all done. So let's see what the results of this code are going to be. So you can see here, here's the original contents of the list. We then add 100 and 200 to the list using push front, which means that 200 comes at the very beginning. Then we go ahead and do a copy. And as you can see here, it ends up in reverse order because we're doing push front. When push back is called, it puts things at the end, so it'll end up in the same order. With push front, it'll end up in reverse order. So just for kicks down here, we could say if equals a list 1 begin, a list 1 end, and then a list 2 begin. If those two things equal, then in that case, we've got end of the world because something has seriously gone wrong here. Otherwise, we can say output is as expected. And there's probably even more clever things we could do here to demonstrate this point. Let's make sure the world does not come to a screeching halt with this example. And the output is as expected. Now, if I really want it to be fun, let's see if I can do something like this. Let's put R begin and R end and see what happens now. That may not work. Let's see. So let's see if I run this and I get end of the world expected. That's actually the result that I want. Yep, that's good. So you can see here that now we can say if it's not the case that the reverse of a list 1 is equal to a list 2, then it's the end of the world. Otherwise, the output is as expected. So pretty cool. Just again, demonstrating how easy it is to mix and match and do changes to your code using various STL algorithms. All right. I think we got one more example to look at. So here's the final example of an insert iterator, one that we haven't actually looked at yet. And this one is going to be the most general of these different examples. This is going to be the inserter, and it's going to use the insert operation. So all the various containers we care about, things like decks and vectors and lists and maps and multi-maps and all the whole variants of the associative containers, they all contain an insert algorithm or an insert method. And what that's going to do is you can basically cause things to be written at the specific location. You can either have it be at the end or the beginning, or actually just any iterator that you want in the collection, and everything will work. Although obviously in some cases it'll be less efficient because it'll have to slide elements around in order to make room for it. So here's an example where you could use a deck. Let's say that we had a deck that had a bunch of elements in it, and then we make ourselves an insert iterator for this particular deck. And then you can say, I want this thing to put the elements at the end. You could also say, I want to put things at the front, and so on. You can control where the various elements go. And then you could also basically have front and back iterators as well. They're just not as generalizable. So here's the inserter function template. You can see what it's going to do is it's going to take an iterator, take a reference to a container and an iterator, and then it's going to go ahead and create an insert iterator object that's going to hold the container by reference, and then it's going to go ahead and make an iterator for the iterator that we've got here. So it goes ahead and makes a copy of it for the type of iterator that we've got for that particular container. So let's take a look at how we could use this particular technique for vector, although it turns out that this is really not the most efficient thing to do because it really wants to put stuff at the end, and we're going to go ahead and have it go to the beginning. So this will work, but it's not the most efficient way to do it. If you use another kind of container, which we can look at in a second, like a set, this would be more efficient. So we're going to make ourselves a vector and a vector iterator, and let's get rid of this explicit code here and make it more auto-friendly. There's an auto-friendly way of doing things, and let's go ahead and use our version that just says 1, 0, 1, 2, 3, 4, and get rid of this silly pushback stuff. So here's the original contents. We print that out as we always do. Now we get ourselves an iterator to the beginning of the vector, and we go ahead and we skip over 2 elements. So now we're sort of like in the middle of the vector. So we've got an iterator pointing to the middle of the vector. And then we're going to create an insert iterator for a vector of int, which we call iter. And again, I think that's beginning to offend my naming sensibilities, so let's just call it iterator. Oops, guess we can't do that. Hold on. Guess we're going to stick with iterator. And then we go ahead and insert rather than overwrite in the vector. And when we're done, we'll print the results. And they should be what we expect here. So you can see here, here's the original contents of the vector. Then we got an iterator to the beginning. We incremented by 2 using plus equal. And then we wrapped that iterator into an insert iterator. And then we went ahead and added those elements at that location. And that, of course, will shove everything down in the vector. So this code works, but it's not really ideal because it's expensive to do that. In contrast, if we came over here, let's go over here and let's say include, I don't know, let's do list just for kicks. We'll make a list here as well. So now we're going to go over here and we're going to say list instead of vector. And you'll just have to humor me. I'm not going to change all the names of a vec to a list and so on, but just pretend like it's a list. Well, the first thing you'll notice is we can't do a plus equal on a list, right? Because it's not a random access iterator. So instead, let's go ahead and do this. This is kind of a little bit cheesy. We say iter plus plus, iter plus plus. So now we're still using bidirectional iterator semantics, but we've managed to get ourselves around this. And then let's say list of int here, because it's no longer a vector, it's a list. So now we've got this. Now let's go ahead and run the code. And we should get hopefully the same results we did before, which we do, which is good. But the difference now is that this is a list. And so doing something like adding an element in the middle of a list, that's a no-brainer. That's very efficient, doesn't cause any additional overhead at all, because, of course, lists are meant to be used in that manner. So I think what I'll do is I'll comment this out for right now. At some point, I'll refactor this code to make this example a little bit easier to demonstrate quickly. But we'll go back to making it a vector, and we'll go back to making this a vector. And we can either keep this the same, or I guess I'll comment it out for now and go back to using the pointer arithmetic random access iterator syntax here, as opposed to doing 2 plus pluses on the iterator to be more bidirectional. Okay, so hopefully that helped to explain this example, and now you should have a pretty good feeling for all the different types of iterator adapters that we have in C++ STL.